Hello, this is Chuck Winkelmann here to explain problem 3 on the Chapter 29B paper homework. The problem reads, a wire having a mass per unit length of 0.002 grams per meter carries an unknown current horizontally to the right. The wire is in a magnetic field of 0.1 teslas pointing into the page. Part A reads, create a situational and free body diagram for this problem. This is my situational diagram. The pink line is the wire. I have my current pointing to the right, and the blue X's represent our magnetic field pointing into the page. This is my free body diagram where I have the force on the wire and a weight force. To solve for the direction of the force on the wire, we have to use the right-hand rule, where our thumb is pointing in the direction of the current, our pointer finger is pointing in the direction of the magnetic field, resulting in our middle finger pointing straight up in the direction of the force on the wire. Part B reads, what current in the wire is needed for the wire to be in magnetic levitation? Our fundamental equations are force on wire is equal to current times length times magnetic field times sine of theta. And our second is Newton's second law, the sum of forces is equal to mass times acceleration. First, we have to solve Newton's second law using this free body diagram above, where we have our force on wire minus our weight force. We also know that our mass times acceleration is going to be equal to 0, as the wire is levitating and not moving anywhere, making our acceleration equal to 0. The force on the wire is equal to mass times gravity. As stated previously, our force on the wire is also equal to all of this, so we can set mass times gravity equal to all of this and solve for current. As you can see, our sine of theta is equal to 1. This is because the angle between these two forces is 90 degrees. This results in this equation. Our mass per unit length is given above in grams per meter. However, the SI units are kilograms per meter, therefore we have to take that into account when plugging that number in. Then we have our gravitational constant and our magnetic field as given above, and we solve for the current to be 1.96 times 10 to the negative 4th amps. Part C reads, find the total magnetic field, magnitude and direction at a point located 10 centimeters on top of the wire. A free body diagram is expected. This is my free body diagram of the point where I have my magnetic field of the wire, and in the opposite direction I have my magnetic field of the external magnetic field. They're opposite directions because at a point located right here, we have this going into the page, and using the right-hand rule, we know that the magnetic field generated by the wire is going to be going in kind of this direction. So at a point right here, we'll have one going in and one coming out, therefore they are going to be in opposite directions. Our fundamental equation is going to be the magnetic field of an infinite wire is equal to mu naught over 2 pi times current over radius. We plug all our numbers in, we solve for current in the previous step, and everything else is given, and we get to the magnetic field of the wire is equal to 3.92 times 10 to the negative 10th teslas. Finally, to solve for our net magnetic field, we know that they're in opposite directions, so it has to be a difference between the two, and the larger one is the external field, so we're going to subtract the field generated by the wire from the external field. Now solving this out, 3.92 times 10 to the negative 10th is basically irrelevant, so we still end up with the same 0.1 teslas, and we know that that's pointing into the page, as stated above. Therefore, our final answer is our net magnetic field is equal to 0.1 teslas pointing into the page.